In this video and the upcoming videos, we're going to shift our attention to second-order differential equations. In particular, we're going to focus on second-order linear ordinary differential equations. Recall that for an equation to be linear, it must not involve any powers, products, or other nonlinear functions of the dependent variable or its derivatives. I offer here the general form for a second-order linear ODE, where we have the second derivative of y plus some function p of x multiplied by the first derivative of y plus some other function q of x multiplied by the function y itself, which is equal to r of x. Recall from the video on the classification of differential equations that if r of x is equal to 0, we have a homogeneous differential equation, whereas if r of x is not equal to 0, the equation is non-homogeneous. An additional definition is that if p of x and q of x are actually not dependent on x, we say that the ODE has constant coefficients, and therefore we replace p of x and q of x by b and c, which are simply constants. We need a few more definitions before we can start tackling second-order differential equations. The concept of linear independence will come up a few times in our study of second-order ODEs. You may have seen it in your linear algebra course as well. Let's have a look. So we say that something like c1 y1 plus c2 y2 is a linear combination. And it's a linear combination of two functions y1 and y2, where c1 and c2 are constants. The next concept is that of linear dependence. We say that two functions are linearly dependent if one function can be expressed or is a constant multiple of the other. So for example, if we have 5x and minus 2x, so we have two functions, and we can see that, let's say y1 over y2 is equal to 5x divided by negative 2x, and we are left with just a constant, negative 2.5. So we say that 5x and negative 2x are linearly dependent. The next concept is linear independence. We say that two functions are linearly independent if one cannot be expressed as a constant multiple of the other. So that is, we can say that this equation, c1 y1 plus c2 y2, is equal to 0 if and only if c1 is equal to c2 and where both of these are equal to 0. Let's think of this geometrically. So let's say we want to describe a point in the xy plane. How would we do that? Well, what we could do is describe it in terms of its x and y coordinates. So we might have an x vector and a y vector like this. And what we say here is that the point P is equal to x plus y. And the vectors x and y are linearly independent. That means that we cannot express y as some constant multiple of x. That is that when we are saying go y units up in the y direction, there is no redundant information in that statement. That is, it is not capturing any of the other information that we are providing in the vector x. And this statement here is what we would call a linear combination.